All right. Good evening, everyone. Good morning, maybe, if you're in the US. This will be maybe a different session because I will try and keep it very interactive. Hopefully, you're all in the Software Underground Slack channel in the T22 data channel. That will be my primary medium for interacting with all of you. And we're going to have a quick, tutorial exploration of the segyio and dlisio libraries. My name is Jørgen. I wrote a lot of this. Hopefully that means I'm qualified to dig into the guts. I appreciate any kind of comment, question, something you would like to explore, and well, really, you're kind of in control of this session as a participant. So I figure what we'll start doing, as you can see, I have the chat next to me, so I will be interacting with that as much as possible. That means that you, Laurie, are on the app. Hello and welcome. And to start off, I figure before this, we published 2 scripts in the github.com/jokva/transform2020 tutorial. You can see here this link, Matt pinned in the channel, contains 2 scripts to download the data that I'm going to use if you want to follow along. This is, of course, not a requirement. It should hopefully carry its own weight without it, but it's fun to play around with too, because you can actually see the results and you can get a touch and feel proper. All right, so we're just gonna go over those real quick. There are 2 directories in that repository, one for dlis and one for segyio. I figure we're going to start with the segyio. I've already downloaded these files because especially the penobscot is a little bit big. It's going to take a little while to download, and we don't want to sit here for 30 seconds doing nothing. So this is the script. It's just 2 wgets for the files with an unzip in the case from the Amazon. If this text is too small, please let me know. Right, and then I'll try and increase it a little bit more, but otherwise it bleeds too much of the lines. So try and keep it as small as we can get away with. If you run this script on your Mac or Linux box, you should be fine. If you're on Windows, just copy the URL and download it through a browser or something, or however you prefer to download things on Windows. Okay. So I would first like to point to actually the web browser, because we have tried to write as much as documentation as possible for the segyio, which is hosted at segyio.readadocs.io. Okay. And you can load that up and you can see the documentation and reference here. Okay. I will probably even look up things here occasionally, and I will definitely refer to it. Increase font size. Text size is good. Well, then I'm going to increase it for a little bit more. I'll try and keep it there and see how that works out. So most of this session is going to be interactive, but I'm not going to use the notebook as you might be used to. Instead, I'm going to use the ipython interpreter, which is the project that I think spawned the notebooks. And we'll also write some small programs occasionally to solve particular problems that you want to see. I'd first like to just briefly, I'm going to start up ipython, which is just a little bit beefier interpreter. So I just wanted to talk a little bit about the fundamental design ideas of segyio and the model that it tries to get across. Okay. Parts of those are historical. Parts of those are based on the original requirements when the project was commissioned. Some are accidental, and I mean, it's a software project, right? So it just kind of grows into itself. I'm going to start by just importing it. Oh, actually, let's start by fetching it. So the most common way to get segyio would be to get it from PyPI. Some of you might use virtual environments. Some of you might use Conda. Some use other packages. Some build it from source. However you obtain it is fine, but I'm going to show the PyPI one because it's the by far most ergonomic for this. Usually I invoke PyPI like this. I am not much of a fan of the virtual environment, so I don't use those very much. So I invoke pip this way. If you're in a virtual environment, you would just type pip, right? Install, and then in my case, user segyio, and I would also allow it to upgrade, okay? You see it's actually already installed, the requirement is satisfied, and it's the version 191, you can see here. So if I start up the interpreter and import a package, I can print a version. I apologize, I realize now, for the keyboard, it is a little bit loud. I'll try and keep it as minimal as possible, but you know, if you gotta type, you gotta type. So we're using 191, everything in this session, we'll use this version. There is a new one brewing that has a couple of cool new features, but we might be able to cover those at the end. So you just import the package. The package is available for the 3 major operating systems, Windows, Mac, and on Linux. You can build it on BSD. I have done that on several occasions. I think it still builds if you use that, but then you might need to get it from source because there are no pre-built binaries for it. So what we're going to do is we're going to start by opening a file. That's sort of the first step. To do that, you call the open function. Now, this is modeled after the Python open function. So, is it? Yeah, there we go. So you can see I have 3 files here, and with the normal Python function, you would open, let's say, fetch, right? There we go. And it would have all sorts of options. Would you want it to read only? Do you want it to read write? Do you want it to be in binary mode, right? And then I think it's read lines. Exactly. This is a script from before, but as a Python object. So this is the interface that we model the segyio open after. And let's do the penobscop because that's actually a real file. You can see you get back a segyio file object. Segyio has now determined that the inline number is 189 and xline number or word is 183. These are details that are sort of very intrinsic to the format. It's specified in the 3 revisions we have now, actually in 2 of them because it wasn't specified until revision 1 from 1997, I think, whenever it was released. But these are the default words in the so-called headers in the segyio format. So this gives us a file object, just like we saw before, but it does, of course, not have a read lines thing because read lines doesn't really make sense for segyio, like it does for the Python file interface of that, which is very text and line oriented. Usually when you do this in programs, you want to use the context manager. If you're unfamiliar with the context manager, that is something that you would learn in what would be the follow-up to Rob's intro to Python yesterday. But you would do use something that's called with, right? With segyio open IO. Now what would happen here is that segyio will realize that you don't want the file to remain open once you've done whatever you want to do in this block, and it will close it for you. So for all your programs, this is what you should do. However, it does work without, in particular to support use cases like using the ipython interpreter. The documentation you see at VitaDocs is already a part of the segyio package. So you can access it by using help, the help function. It's very useful. And here you can see the functions or the methods that are available on the segyio object. But this is just the idea of an open file. You can see it has all kinds of methods. These are the methods you would also see when you try and tab complete it. Okay, so let's look at some of the properties that segyio has been able to determine from just opening the file. It does that by opening the file on disk and scanning through the headers and making a few reasonably well-founded assumptions. The file is a big endian file, which means that it has something to do with the order of the smaller and larger parts of the bytes in an integer. The exact details there doesn't really matter, but the point is that with a big endian file on most systems, you would not be able to just read the data as they are as integers. You would have to convert them somehow. So there's a translation phase going on. segyio assumes that all data is in big endian because that's what the first revision said that it had to be, which is something that was relaxed in the second revision where they allowed them to be in little endian. All right, so Michael Harty has a question. How do you run the fetch script? You're on Linux, but still in UB. That's okay. So what you do is what Jorgos here actually proposed is just run in your shell by typing, well, bash and then fetch.sh. That should work perfectly for this segi script. You need to modify the dlis one a little bit when we get to that. If your file had been little endian, usually segyio is not able to determine it. There is a word in segyio revision 2 that you can use to actually determine the endianness of a file, but most files before 2017 did not actually populate that at all. So it's a very poor indicator, and it just doesn't work in general. We can see how many samples there are, and additionally, you can see there are offsets. So this is sampled every 4 milliseconds, and it starts at 0. Some files have traces that start at 200. Some, I'm not a geophysicist, but there are tons of variations there. It has a close method, so you can close the file. And if I now try and read anything from it, I'll skip a little bit ahead and just try and read something from it. I will get an error. And it's an IO operation on a closed file. Usually, we structure our programs so that this is never an issue, and this is where the context manager, the width, comes in. So let's open the file again. This is now a new fresh handle, and it's forgotten everything that we've done to it. Usually, what you want to do, actually, I take that back, but the model that segyio tried to implement is that it realizes that segi as a format really is just a collection of traces that are in some way ordered, right? And that is very similar to the list. This is a list or an array, depending on where you're from in the computer science. But it's a list, right? So it's a series of data entries. Just for reference, in Python, you can populate a list with pretty much anything. This is a list, right? So this is a list of strings. And from segyio's perspective, a file is just a list of traces. Okay, this is before any interpretation is going on, but that is the fundamental structure. So that is the fundamental model that segyio tries to expose. To do that, it has in segyio we call them modes. They could also maybe even be referred to as views sometimes. But it has one that's called trace, right? So this is a trace object. It is the view of the file as a collection of traces, or just as a big on-disk array of traces, okay? And since it's really just that, it of course supports trace operations, list operations. The most obvious, of course, is indexing. So if you index into the trace view, if you will get the trace. And like in a list, traces are just ordered and indexed by natural numbers. So you can do the first trace and the second trace like that. If you look at what you get back, that's an ND array. So segyio was built with the philosophy that it wanted to give the power to you as a user and get out of the way as soon as possible. So segyio, in fact, implements very little mathematics or operations you would typically do on seismic. It says, I'm going to leave implementing that to you. You only need to support it for arrays, and I'm going to give you the data. So in that sense, segyio is a fairly low-level library. Don't get me wrong, it does a lot of work for you to try and feel high-level and feel abstracted and feel easy to use. But the fundamental model is just to read traces. It doesn't interpret them in any particular fashion. It doesn't give you any of the operations you would normally do on your seismic volume. And that's why virtually anything that looks like data will immediately be an ND array. And that's a good thing. So let's get the first trace and just store the array in an object. Let's get the 1024th. All right. So this is some data. Obviously, it's just a lot of floats there. See, there's probably nothing measured at the top. And this is just an NumPy array. And since it's just an NumPy array, you can do whatever you want with it. You can sum it. You can average. I guess that's not it. It's mean, isn't it? Yeah, you can average it. If that would make sense for you, right? So you can do all sorts of cool things. But since this is just a NumPy array, you can do any maths on it. Segyio does not actually interfere with that at all. But if you notice, just getting the data was fairly quick and easy and painless. One of the problems with segyio is that while it's a quote-unquote standard, it's only a standard for representation. It carries fairly little semantics that isn't highly specific to the file, and very often relies on a lot of data that is not in the file, which means that as a library, it is impossible for me to actually make that decision for you. This means that segyio can only present a model to you where it makes it easy for you to get a faithful image of what's in the file, right? So we're trying to just faithfully report this is what the file says, but it's up to you to make sense of it, which means that we're not stripping any nonce. We're not trying to interpret these zeros here as something in particular, even though it's probably just not a valid measurement, right? And even when the standard says that something should be, more often than not in practice, it doesn't work like that. You know, segyio as a standard really doesn't exist. It's the basis for a dialect for a file format. Okay, so let's go back to the array model of segyio. So the fact that you can now read any trace in the file. Actually, let's see, how many traces are there? Let's ask that. So since this is meant to provide you the idea that it is basically an array, that means you can do len on the view itself. One of the motivations for doing that was that we wanted people to be able to prototype and experiment with their program using small in-memory arrays, and then pretty much replace the array object with segyio and have the program work for files. Of course, it's not a perfect match, but we figured that would be a very quick and easy way to actually develop sophisticated software. And you can see it has 289,081 traces. So let's try and actually access that one. We get an index error. It says out of range. This is This shouldn't be very surprising if you're used to working with lists in Python, because if I make a list of 4 elements and I try to access the 4th, it will give me the list index out of range. And the value 4 is at index 3. Like arrays in Python, the traces are 0 indexed. Which means that if I would do this with the 0 instead, I would actually get the trace from there. Makes it all zeros, not very interesting. Like with lists, you can use negative indexing to achieve the same thing. And just do, well, actually, it's a lot of nothing at the end there. Let's do 10,000. Oh my goodness. Really should have figured out where the hell there's data in here. So let's do 10 to. All right. Turns out there's a lot of zeros in this file. That probably makes sense. But regardless, you can do negative indices. So actually, let's go back to this one. And we just put a minus in front. And now you see we have some data. And actually, we saw this one before, because this should be, I think, 1. Yes, 1. Which I think is pretty neat. So the traces, they actually behave like arrays. Interacting with segyio and segyio files in this manner will more or less always work. Okay, there is one fundamental restriction in segyio, and that is that all traces must be of the same length. In practice, this works very well, but there are very exotic files out there where traces are of varying length as well, but we don't support them. We don't support them in order to make this fast. Like arrays, we support slicing. You can see if you do 1 to 5, you get a generator object back. This is just Python for something that you can iterate over. You can just print it, actually. So this is pretty neat. Now we can have segyio just present the 5 traces for us. And of course, the trace view supports steps, which I think is pretty neat. In some cases, actually in quite a few, segyio files aren't just a bunch of traces, but they try and model a cube of volume. Now, segyio has some requirements for what it considers a volume, in terms that all in and cross lines should be unique, and it should be fairly well ordered in order to make addressing and indexing fast. But if your file is sufficiently tidied up, which it often is in PostStack, then you can use segyio in a more sort of geometry-aware fashion too. And there's a question here from Anne. Hello. Do you have a way to detect traces which have funny lengths and remove them? Not from Python for now. So all addressing is done implicitly with the assumption that you can figure out the length of each trace by counting or reading and trusting the number of traces that's in the header, figuring out how big the rest of the file is, and then compute it and say, does that number evenly divide? Well, that's the number of traces, right? It's just division. If that fails, then at least one trace have a funny length. So detecting that isn't hard, but figuring out which one out of potentially millions of traces can be pretty difficult and time consuming. And we don't do that by default. And in Python, in fact, it's not done at all. Building a program that would detect that is not very difficult in C. It's or using the C features, and in fact, some of those C features are available in the Python library. So writing that program isn't too hard, but the thing is, what does it mean to remove them, right? What decision can you make that will actually be right for all cases? Probably that is very file specific for your application, which is why it's not there, because you need to write it custom anyway. And well, we figured pretty early on that giving out a sharp tool like that would be counterproductive, because the considerations you need to make they're non-trivial. You need to basically phone your neighborhood programmer to help you with it anyway, right? There's a lot of things that can go wrong, and there's a lot of very quickly into undefined territory issues that quickly arise. So that's not there. However, doing it is not particularly difficult, assuming you can trust the data. Okay. One thing that's worth noting, and that makes Segway occasionally a nightmare, is that it has the so-called trace headers, which is metadata for each recording, each trace, interleaved with the actual data. This is a problem for many reasons, because for one, it prohibits very effective and efficient reading of data, because you can't read in big chunks without doing filtering and weaving afterwards, which fragments your memory and cause all kinds of slowness. But there's a lot of very useful data in that. And if the trace is just a series of numbers, then the header is just a dictionary, which, and in fact, the headers are organized the same way in that they're just consecutive, right? So the collection of headers is a list, which means that since it's just a list, you can do list things with it, like slice it. The header list interface support actually the same, let's choose that one again. It supports the same slicing and sequencing that you would expect from a list. And in fact, it implements the list interface. If you take a look at, actually, let's do this, how. If you look at the header object, you can see what it does, and you can read some of the documentation. The header is really, it's a dictionary with a very specific set of keys that are always the same. And the Segway header object actually reads and interprets the bytes that are the raw header and give you a much more practical interface for it. So let's have a look at one of those. Right, so just get the 10th header. And since this is a list, or so it's actually the 11th, but it's the header 10. So, and since it's a list, we can just index into it, right? And that gives us this noise, which is just the dictionary print. There is a cool Python module, it's called pprint, or pretty print. And since the header is just a dict, it should also support pretty printing if you dictify it. Let's see, it's 10, isn't it? There we go. So there you go. It's just a way of interactively printing it in a nicer way. But usually in your programs, you do interact this with the specific keys that you care about. So Tony, hi. One thing that confuses people with the header is that the keys are enumerators rather than string. Can you elaborate on that decision? Yes. So there are a few pretty damning, I would argue, design flaws in Segway, and I think the use of enumerators is one of them. Given the chance, I would revert this, right? But there are a lot of things that do rely on it now. So one of the problems is that we wanted to cater to people that didn't really use. All right, so the first problem is that the Segway standard does not actually have identifiers for these. They have descriptions and they have the offset into the header. And that's why you get stuff like, so let's just print the summary or the representation thing for the file, you see it says I line 189, X line 193. A lot of people that have spent a lot of time interacting with segyio files, segyio experts, are only familiar with these offsets, right? They talk about words and offsets as if it's the same thing, which arguably kind of is. And we wanted people to be able to take their old programs that they had written with these numbers directly, these offsets directly, and have them more or less just work with segyio. So we needed a way to almost implicitly translate from an integer to a richer object. We introduced then the enumerator because we wanted something that was quote unquote safer than just a bunch of strings going about. Honestly, I think that has hurt us more than anything because what we should have done is to just do mappings directly, just have a huge dict of both the string and the integral representation and just looked it up. That is a much better way of phrasing things in Python, and it would avoid this confusion with the enumerators. Also, enumerators in a language like Python, which isn't type checked ahead of time, suck. They're terrible. No program should ever use enumerators, and I will fight you on that. That it was a huge mistake. Should not have happened. We've tried to fix that a little bit with some of the new interfaces, with the seismic Unix interface, and when we added the dict methods. We tried to fix at least that partially for a much more natural way of going about, I think. So we're getting there, but now we're in the problem where we can't really take it out either because of backwards compatibility. But yes, huge mistake, shouldn't be enumerators. They should be both strings and integers. We wanted to give the idea of type safety and auto-completion. So what you can do is like trace field, for instance, and then CDP. You can actually now autocomplete the CDPX. Right? And now you get actually back the integer 181. And I mean, you can get 2 bytes because this is a primitive byte-like object. Oh. Yes, I'm going to mention the seismic Unix interface again. I'm going to cover that. So anyway, let's just get the pretty printed header back. So at the end of the day, the individual headers are dictionaries, and they do behave like that, which means you can do all sorts of things with them. You can do keys, and that gives you a list of the keys. And of course, shouldn't be surprising that this always gives you just a list of the fixed set of keys, right? You can do values, and you get the values. And this is a values view with trace sequence line, field record, and I think it's items, right? Pretty cool. This works the same way for the binary header, which is also just a dictionary. So the binary header is sort of the global set of parameters for that file. A lot of these stem from the time where the segyio was designed for seismic lines. Later on, it sort of cubes was just folded in there. Regardless, this is still just a dictionary, which means you can do all sorts of dictionary things with them. And in fact, if you in your notebook or in your ipython or whatever, try and autocomplete them, you can see all kinds of dictionary methods in here. Of course, some won't really do anything because it's a fixed dictionary. You can't pop a key from a fixed dictionary. One thing you can do, though, is you can update. So let's go back to the Python dictionary. You have a thing there called update, where I can do, let's say, I think this is it. Keyword can't be an expression. Yeah, there we go. Oh, that's even a none. All right. Let's see. We do 1, 2, 1, and then we do geo. Yeah, that's so Matt points out that it says Segway revision 256. This is a file from the future. It is also a file filled with garbage. So it's probably either meant for something else or just filled with, I actually don't know what. But okay, we have a dictionary, which 1 goes to 1 and geo goes to awesome, which I think it does, which we can update. And I think this should be it. And you see we added a new string to the dictionary with the value 2. So that's something that we can do in the binary as well. So let's actually try that. So if you look at the keys, it has, for instance, let's take one that doesn't break it. Let's do the correlated traces. So this is dictionary, and we can look up the correlated traces. The correlated traces is actually not defined. That is the enumerator, and this I think is what Tony was referring to, is that it's awkward. This should probably work, right? But in the trace field module, the enumerator is defined. Here we can find the correlated traces. Isn't it trace field? No, sorry, this is bin field. Correlated traces. And you can get the value, it says 0, right? To write it, you would do what you do with a dictionary, right? You would write something like 10. But now we get an operating system error because we can't write to the file because we didn't open it in write mode or writable mode. That, fortunately, is easy to fix, and we'll get back to that in just a little bit. Actually, I think we'll skip a little bit ahead and go to that now. So let's exit the interpreter, and you can see the penob scot there. We'll copy that, just not to ruin it, and then modify penob scot. And I think this is a pretty good time to point out that segyio, in terms of writing, was primarily designed to in-place edit files, not really create them from scratch. The assumption there was that if you wanted to create segyio from scratch, you needed to take a lot of care anyway, and it was usually done as a result of a lot of maths and processing going into it. Segyio can create files from scratch, but doing that means you need to make a lot of decisions, and you need to populate a lot of header information that you probably never really think about being there, at least not in your day-to-day life. So we need to import segyio again because we tore down the session, and we need to reopen the file. But now what we're going to do is we're going to do the modified penob scot. And then we're going to open it in a different mode. We're going to open it with r+ like the error message suggested. So this interface was stolen from the Python open function, which uses this mode argument. Python in turn stole that from C, and I don't know where C stole it from. I don't know, maybe they invented it, but it's definitely older than Python. Now what is different is that the file is actually writable, which means that what we can do is that we can go now into the binary header, and this, Tony, is why we do the enumerators. So you can tab complete here, because no one ever actually remembers what these keys are called. And they don't have names in the standard, so we needed to make them up. So it used to be 0, and now we just do 10. This carries no specific meaning to me. I'm just making up random numbers, and 10 is pretty nice. And now we can actually observe, once this is flushed, that the file has changed. So let's actually do that. Let's Let's print it. Now it says 10, where it used to say 1. And in fact, if I open the source, sorry, modified. If I open the source, oh, sorry, I didn't mean modified, I meant the source one. You can actually see, though, open it again, that the right thing, sorry, the right has happened. In the original one, it was 0. Now it's 10. So writing individual fields to slightly modify and tune a file is very, very easy. Of course, the binary header has a lot of keys. It has 30 of them, actually. And you don't want to do that 30 times. You don't want to do that for 2 reasons. First of all, because header writes in segyio are atomic, which means that when you write the full header, even if only one field is updated. And second, the code to do that is ugly. Because what if you want to do, let's say you have interval and samples in the original, right? Let's see what those are. Sample. So this is a pretty cool feature that hardly anyone ever used, but you can actually look up multiple fields at once. And what you get back is a dict with the numerator and the value, but both of those are 0, right? And sometimes what you want to do is just update both at once. So let's do that. And this is, right? But here, you, if you look at the updates documentation, this is actually just stolen from the Python docs. Here you can see the usage. And with enumerators, with integers, you get a problem when you're going to use this update interface because it doesn't really support it, and it would be different from what you would get from a dictionary, and we try to be faithful to what you would expect from Python. And this is where the SU comes in. So Seismic Unix do set a lot of these names for header words that have been in use in the industry for a very long time. And we reuse that in order to make the update work. So you can, they're all hidden away in the segyio.su namespace, okay? And here you can find them. And I have to admit, I can't really remember what the interval and samples in the original are. I think it is HNS or ONS or something. If anyone remembers, please write it in the chat. It's NSO. Okay, there we go. So it's 3223. Bin field samples. No, is it interval original maybe? No, that's not it. Yeah, there we go. See, number of samples original and samples original. They're the same key. So this is just an alias. The Seismic Unix interface is just an alias. But you can use those words in the updates. So we can do app.bin update, and then NSO is 10. We like 10. Actually, let's do 12 for good measure, just so we have something different to look at. Now, if you print with the same accessor again, you'll see now that the samples original has changed to 12. Using that, you can update as many header words as you want in one go, which is more efficient, and when you're working like this, a lot more ergonomic. This was decided upon when I started realizing that people use segyio a lot more as an app than I expected. I expected it to be a low-level library for application developers to be able to take segyio as input data. it turns out it is very useful on its own, and there wasn't really anything like it available. So it gained pace that way. And this is one of the features that we've added in order to support that use case. This, of course, works exactly the same way for trace headers, so I'm not going to show that. But this is pretty neat. Okay, so enough about the headers. They are dictionaries, they behave like dictionaries, and they're predictable like dictionaries. If they're not, please file a bug report. A lot of segyio files try and model volumes, right? They have some structure, some geometry tied to them. They're usually called inlines and crosslines, what we're working with here. And like the trace view, we have an object which is called a line, which is no longer an array per se. It is a sort of ordered dictionary. The inlines object that is on the file just shows you the numbers that you can use for indexing. And this is actually a very neat volume because they start at 1,000, the inlines, and they go up incrementally by 1. Okay? And you can just pick any of these numbers and index into it. This gives us back a NumPy array with the shape 481 by 251. Now, the 251 is something that we're going to see a lot because that is the number of samples in the file, which is pretty cool. You can do the same thing for crosslines. See, right? And crosslines. They too actually start at 1,000 and then that's 1480. Which means that we can actually use the exact same code for the crossline. Notice that it's still 251 here, but this 601 is now different. This is really just segyio trying to help you write your program in a line-by-line fashion without you having to do the manual loop of looking through the headers, determining if something belongs to the same line, and having all that ordered. It uses a few assumptions to do that, which means that it can be wrong in very, very, very particular circumstances. But so far, I've never really seen that happen. The fact that this is a multi-dimensional object, see, with the shape, you can do all sorts of cool things with it. But this still is an ND array. So this is the philosophy where segyio just wants to give you the data as soon as possible in a reasonable format and then get out of the way. So this you can do, all you can do with ND arrays because it is an ND array. We're not trying to do any mass view here. The alternative would typically be that you would have to write the loop yourself and then gather up. And for well-formed files, we're able to do that for you, which is very convenient. Like traces, let's do 1260. You can slice these. And now you get a generator of lines. You can do for line. Just going to print its shape because otherwise my screen will be very full. And you can see you get, where's that? 12 objects with the same shape. Of course, the data is going to be very different. So just to demonstrate that, let's just do the mean. You see you get different means, right? Of course, mean is probably not something you would do on a line, but it's interesting here just to demonstrate the fact that each array in this iteration is different, and it is a different line every time. So that's a line. It works the same way for cross lines. You can slice it, you can step it, and it's pretty great. But at this point, I think this feels a little bit underwhelming because as an interface, it doesn't do anything that you haven't already seen for traces. But if you think about what you're now able to do is that you're able to process a volume line by line in, sorry, this very simple loop, right? And we've done, segyio has done all the structure for you there, and you don't actually have to care about it. So you now have a very simple program that does something that is somewhat sophisticated. Okay. Just for reference, there is the Seismic Unix module. If you run help on that, you will see both all the keys that are there and the integers they map to. And there is also file feature. So segyio is almost a misnomer at this point because we also support Seismic Unix files directly. This was a feature that was requested by Filippo. So shout out to him for doing that, because it's basically a broken segyio with some different assumptions. And it turns out implementing it was not as difficult as I had feared at some point. Seismic Unix files work pretty much the same way as, Seismic Unix files work pretty much the same way as segyio files, except they don't have the text header. So that's really it. Okay, there are a few more features that I would like to show you. If there are anything in particular you'd like me to demonstrate, I'd be very happy to do that. But one comes from, let's see, are there any other interfaces planned from that? Not as of now. Well, actually, there is one, which is, it's still a little bit experimental, which is one for groups, or in practice, what you would use it for is shot gathers, but it applies to really any group. So one of the interfaces, let's see, I'll just pop over to the documentation real quick to see if it is there. Yes. There are two interfaces, actually, that I would like to show that I think are pretty cool. So that is a very good question. So one is the gather. Okay, and the gather is a misnomer at this point because this is not for the shot gathers. But this is for the case where you have a file, which is post-stack. It is fairly well processed, but you still have offsets, right? So, which in practice, the model that segyio has for that is that you have the same cube, just in parallel. You have multiple parallel cubes for each offset. This file actually does not have it. So sorry, this is for pre-stack. This is no longer post-stack. So it's well processed. It should be fairly sorted, and it has to be regular, but it's no longer post-stack. It's pre-stack, which in turns is this parallel view. Of course, you can use the gather on post-stack files too. It's just not interesting because it pretty much gives you access to two-dimensional indexing with the appropriate with slicing too. So in this case, you only have one offset. You can actually see that with offsets. You only have one offset, which is 0. Right? But that means that you can do. And for post-stack, this means that you can pretty much say, I want to go to this intersection of the lines using their line numbers, which allows you to put yourself pretty specifically into a grid. So let's do 1200 and how big was it? Actually, let's do 1260 then. Yeah, let's do 1260. So this, I think, is in fast, slow offset order. this right here is now the trace at inline 1200 and at crossline 1260. And this is pretty cool because you can do this with ranges. So let's just do 05 and 1265. This is a generator object like before, because whenever you slice something here, we want to do the generator because reading it ahead of time could be very, very large. And we want to defer the choice or the time when you're actually going to read from file. And we're going to defer that choice to you because you might have some performance consideration in your application that I don't know about. And with the generator, you always have the option to postpone, but you can also do it immediately if you want to. And here you go over that line by line, which I think is pretty cool. Can even do shape. Oh, sorry, trace by trace. Trace by trace. Yes. Isn't that cool? It does this in a in and then cross line fashion. So you of course now need to untangle a little bit if you want very if you want to reestablish the geometry. But of course, this you can collect and then reshape if you want to. And this effectively allows you to get a subcube from wherever, or sorry, to any point in the file using lines. The other one is the one that is called group. So the group is a fairly new thing, and it is still experimental. Notice the emphasis. The group is pretty much a pre-written scan where you say, please give me all the traces with header words that match my criteria. The main feature you would be looking at there is the shot gathers, where you're looking at the geophone number and some other usually. And when those two correspond, then they belong to the same shot, right? Of course, you can use this feature to implement most of the other features in segyio, but this assumes that you are in a case where you have very little regular structure, so you need to do scans. It's very slow in the worst case, but if you need to look at a full pre-stack unorganized volume, which is really just a bunch of shots, you don't have any structure to rely on anyway, and anything you do will have to fall back to being a full scan of the file. So as it says in the documentation, it walks the headers and groups tracers in two buckets where they match the words. So there should be some examples for that too, and it's pretty cool. This actually was a feature that was devised for Transform 2019, and most of it was implemented there. See, is this the latest? Looks like the reader docs is not actually updated because this is for 1.8.8 and not 1.9. But yeah, so this is actually a direct consequence of the Transform 2019 conference. Shout out to France, shout out to Normandy for that. So what you would do is that you would create a group, which is a method. Let's see, it's interface, and then on the word. Okay. So the word, let's actually do one that we know. So we do on the word 189. So this is now the integer for inline, but you could of course use segyio.stu.inline as well. Or is it iline, I guess? Yes, there we go. Now what you get back is a group. Let's call it grp group. And you can see this now is a lot slower than all the other reads that we've done so far. And one of the reasons is this actually is the full file. If you look at what it has a few things that are largely internal. So let's forget about the fingerprint for now. But you can look at the items, which is still a generator. And here you can see the value of the buckets that it finds. So what it does, it goes over all the traces, and it says it creates a generator for each of those, or a group for those that match the key or match that value in the word that you're looking for. Okay. The key is 189, and that's so you can be able to actually just get a group object from anywhere and ask what is the key. And like the segyio file, it has the trace interface again, which is just a list, which I think is pretty cool. All right. Yeah, these are the bins that they're in. So if you, normally what you then would do is that you would go over these by items, right? So you do for G. You've seen this before, right? And actually, if you look at the last one, you can see the count. And you can do the index. Oh, right. I have to admit, I haven't used this feature very much myself either. But it is very useful because the group, when you make it, don't have to be just one key. It can take an iterable of keys. And now this scan is taking even longer, right? And this, I think, is where it shines for the pre-stack, because then you would do geophone and then something, right? And then was it bins, I think? There we go. And here you can see these are really just the intersections. And then also the trace index that of that intersection. So I think this would even be it. Let's actually try that. So we do gather of 1002, 1037. You print that. And you check if it's the same, and it was 999. And it's the same, which is pretty cool. So this is just a shorthand for that job, which you would have to otherwise do manually. Again, the interface, as you could see from me struggling a little bit with it, is still a bit awkward for some of the internal details. But for the please filter into these buckets for me, it's pretty convenient. I'll try and get the documentation updated so that version 1.9 is also available on the reader docs, because there are some good examples in there. Okay. How are we doing on time? So we've been doing this for an hour. If there are any more questions then, or things that you would like me to demonstrate, I'd be happy to do so. We can, of course, also come back to it. But I am now going to get a glass of water. So we're going to take a 3-minute break. And after that, I figure we'll dive into dlisio, because that too is a massive package that we haven't talked enough about. Okay? All right, thank you very much. All right, welcome back, everyone. That was just a brief water intermission. We'll plan on an actual break at 30:30, so which is in 20 minutes. And I think I'll take Evan's questions and maybe a little bit more before we then wrap up segyio. So Evan's question is, what are some of the options when you try and read a segyio file and it doesn't work? Can you explain what strict false is doing? Yes. So I guess the first thing you do is despair, because when things don't work, it's very frustrating, and it's just, I mean, you're kind of at a loss, right? But the first thing you want to do is look at the options that segyio open has and what they actually mean. So the first option is the file name, which is just the file path, or the path to the file in your system, which is, well, I mean, it should be pretty self-explanatory. The mode is whether or not you want it to be writable or not. You should really only ever use R and R+. And I think if I were to redesign it today, we would have a different interface for it. So those two are pretty much never anything you want to work with. By default, segyio opens in read-only because that is the non-destructive option. If it was read-write by default, it would be very easy to ruin your files. It has two more arguments, which are in and or iline and xline for inline and crossline. And they default to the two header words that are specified by segyio revision 1. So those are the words that you want segyio to use when it tries to establish a geometry. Geometry is what it needs to be able to provide the fast in and crossline interfaces that I showed you earlier. Now, usually 189 and 193 are the words used for that. But in a lot of pre-revision 1 files, the words 5 and 21 were used, and they were used exactly as inline and crossline words are used later. So if you know that about your file, that it is supposed to be a proper cube, it is a volume, it is well sorted, it is well organized, and it's very structured. It's just that the line number is not in the 189 and 193 fields. You can specify which field you want segyio to use. And that's just a word that it will look when it tries to determine the geometry. Now, what strict equals true does, which is on by default. So this is a very old design decision. So in the first, when segyio was first commissioned, the request was a library that would allow our people to work with post-stack files. They were all volumes, they were all neat. There was never really an intention for segyio to work with non-sorted files. Turns out there are a lot of non-sorted files out there, and that it is very useful to be able to read them. But at that point, segyio was released, it was considered stable, and we wanted the default to be what you would expect, and you wanted the maybe sometimes surprising thing to fail on you by default, which is what the strict argument does. So by default, segyio assumes that what you give it when you use the open interface is a cube. It is neatly fixed volume. And what strict equals false then would do is say that, all right, if you're not able to establish a geometry, you know what, that's fine. If you can do it, that's great. But if you can't, just at least give me access to the traces. All right, so this was the graceful failure, if you want. So yeah, I couldn't do everything I wanted to do, but I could at least do this so you can check why is this not a proper cube. Later on, it turns out that's very slow because it means you need to scan. And sometimes you already know ahead of time that this is not a sorted volume. It is just a bunch of traces, or it is a shot gather as ordered files. So just skip this trying to build geometry nonsense because you won't find any anyway. And I know that ahead of time. And that's the ignore geometry argument. They default to true and false because that's how segyio first operated. And that's in order to not break programs between versions that were written against that assumption and interface. And then there is the endian argument, which is say, if you know that your file is little endian, please let me know too, because up until revision 2, there was no header word that you could query to determine which one. And when you're looking at bytes, it is virtually impossible. It is actually impossible, unless you know something about the data and how it should be, to distinguish between a well-formed file and a broken file and garbage, because it's just bytes. So unless you know exactly what is supposed to be there and what it's supposed to look like, you're actually not able to tell. So we need you as a user to know that and tell us. Most of this we try and describe in the documentation. This is also the same docs that are available at Read the Docs. Okay. Oh, hello, Chance. How are you doing? Yes, yeah. Okay, so there is a couple of cool other features that really aren't much talked about because they're kind of niche, but they're very useful when you actually need them. So one of those is the one that is called trace.ref. And the trace.ref it's a write back, or it says there in the documentation, it's a write back version of trace. So what you can do, so F is still now the modified pen obscot, and you see it's opened in read write mode. So one thing we can do now is that we can do for I trace in trace, and let's just do the first 5. And actually, this is an enumerate. So for I trace in trace, and the first 5. So now we print the index of the trace and the actual trace itself, and you can see these numbers are all over the place. Okay. One thing we can do. Oh, and sorry. In order then to actually update it, so let's do that to the first 2. What we can do is that we can do, let's see, f.trace, and we just write the value, but we need this to be an NumPy array or some array-like, so we do list. Actually, let's just do this. I for all right. So what we're going to do now is we're just going to write the trace index as the only value into the trace. Okay. After printing it, and now if you do this, do just the printing a second time for the first 2 traces, we should now see 0 and 1. Which we do, right? Now, this is kind of clunky because it requires you to copy out a couple of times, but more importantly, it requires you to keep the index. And for a lot of applications, you kind of don't care what the index is at all. So what you can do is, let's go from 2 to 5, just to get a bit more. And we're actually going to keep the enumerate. We're going to start the enumerate at 2, just so we can get the continuing. And then this is no longer trace, but it's trace.ref, which is a pretty cool thing, I think. And the idea is that we should be able to do this trace.assign. If anyone are super good with NumPy, then right. So if we have an ND array like there, we do trace. I think it is assign. Fill. It's fill. Okay, so you can do fill with 10, and what you get back is just 10s, right? So this is still just an in-memory array. And the idea is that you can use this ref interface. This exactly won't work. But what you can do is hang on, I just need to look that one up. I think it's even here, just so I get it right. Data trace ref. Yes, there we go. It turns a ref trace. There we go. So you can do two to five. I think it's this. So now you need to do with trace.f.trace.ref. There we go. Trace in, and then with the I. You need to remember the I because we're going to enumerate. Enumerate from 2. Then we can do trace.fill. So what we're going to do now is just update the array in place. This was remarkably slower than I thought it would be. Oh, because we did all of them. All right, so this entire file is now broken. So now if you see, if we just go into trace 2, you can see all 4s, which is pretty cool. It started at 2, remember? That's why we're getting the offset of 2. And what that means is that when you're in this context manager, you will be able to actually update the data in place instead of having to preserve the index, which allows you to do some pretty nifty pieces of code, for instance, to merge or copy parts of a volume without having to dealing with, well, indices, which used to be the only way to write back data. This is particularly useful when you're creating files from scratch based on some algorithm. It is very useful when you need it, but it's quite niche, I think. All right, we have about 8 more minutes before we're at break time. Until then, I want to use that time to just briefly talk about the tools module. So the tools module was intended to be a place where both we and community could write fairly common, maybe special purpose, maybe slightly sharp edges tools for use with segyio, which means that the requirements for correct in all cases are the restrictions are much looser. I think the most used function from there is the cube. So the cube function, for instance, is designed for whenever you know that you have a fairly small file, does fit in memory. All you want to do is to just grab a copy of it as a NumPy array. You can do segyio.tools.cube, and then a file path like this small that I know is there, right? And then small. What I now have is a 3-dimensional and NumPy array, which is just all my data. Of course, this is not feasible for huge volumes, and it also assumes that it is fairly well structured, but it's pretty convenient. What's neat about it is that it also takes file handling. So you can do the mod panob .shev, and you can see I've now read this from the file handle. This allows you to work with files where the inline crossline numbers are different from 199 and 193, because you open it, you adjust that, and then give it a file handle, which is pretty neat, because now we have all of that as a NumPy array. So this is for those quick and dirty jobs, right? And then you're immediately in NumPy territory, which is nice. It has some function for figuring out, well, actually it's mostly used internally, but figuring out the sample rate. And there's also the from array functions for which is a family of 3 functions for whenever you just have an array, you just want to dump it to file, you don't want to add very many or deal with 9 numbers, you don't care about coordinates, you just want to store your data in a way that segyio can open again at a later time. So that's the from array. It creates a file from an array. It's very useful. There's also, I think, one more, which is actually two more that are quite useful. One is the metadata that creates this spec object that you can pass to create, which we haven't talked very much about, but it allows you to very quickly get enough metadata about the structure, about the reach and line numbers and shape of a file, so that you can create a file with the same shape, which is very useful if you want to map whatever you're doing on your volume into a new segyio file that has the same structure. But for instance, with when you're computing diff traces, would be a good example. So you have 2 files and you want to create a 3rd file, which is just the difference between the 2. And of course, they have to have the same structure. And then this is a pretty good way, or pretty easy way, of just getting a file handle that would, when you write to it, give a file of the correct structure. There is also, all of these are documented, but also rotation, which gives you the northing, easting, clockwise rotation of a file. Which it's pretty much just a loop that chases the first line and determines the difference in CDPX and CDPY. All these are documented in the tools module for these small but sometimes very specialized tasks. All right. I suggest we do a 10-minute break now. It's 5 minutes to, so we'll start at 9:35 Central European Summer Time. Which is Norway time. We'll do a 10-minute break now, and then we'll start with dlisio when we get back. All right? Thank you very much. All right, everybody. Thank you and welcome back. I think that should conclude segyio, at least for now. But of course, if you have more questions, then I'll be very happy to answer them. I would just like to end that segment by just saying what an incredible mess that segyio is. It is not a standard format, as I said, it's a dialect. But if you ever want an actual reference implementation SEG, just phone me one day, okay? All right, so pitches aside, let's have a look at dlisio. Now, dlisio is much younger than segyio, and it builds on all the things that we learned doing segyio, and it tries to, address at least some of the shortcomings. But I would like to preface all of this by saying that dlisio 2 is a fairly low-level library in the sense that it doesn't try and do well-log interpretation for you in any way. It's a library that tries to faithfully give you what's in the file, but in a convenient manner without having to bog you down with all the details. Like segyio, you can find the docs at dlisio.readerdocs.io. These are largely written by Alan, who I think is in the chat, and big props to him because he is the maintainer of this project. dlisio tries to read files in the digital log interchange standard version 1 only. Version 2 is still out of scope, and the formats are sufficiently different for it to need a completely different approach and library anyway. And like in the log ASCII standard, the S should probably be soup or something, because it's not really a standard in practice, because guess what, just like segyio, it is constantly violated. So one of the things, we're just going to start with just this fetch script, which I'm just going to write to my screen now. There are 3 pieces of data here. 2 are a part of our test suite. For this, you can just get here with, if you're on Windows, you can just copy this address and paste it into your browser. The one from Volva, you would have to use something that called the Azure CLI or Azure File Explorer or something to get. Doing that, unfortunately, is a bit of an exercise, and I don't think I'm allowed to rehost the file. So I've copied the method from Matteo Ravasi's notebook, and you can do that. Your SAS token is everything from SV up until and including the SP equals RL. And if you paste that, or you assign this variable SAS token to that, then this script should just work by running it like before. So yeah, these are the files I'm going to work with. But really what I'm just going to do is I'm going to explore them a little bit and try and just tell you a little bit of what exactly is in a dlist file, what is the structure, and what is it you should look for, and what kind of a mental model should you have for this format. Okay, so dlist files are for well logs. And in practice, what you will find is that most of the logs that are hidden in dlist are of much lower level and much less processed than you would typically find in LAS files. Why that is, I have to admit, I do not know, but dlist is a lot richer and it's a lot more powerful than what LAS is. So my guess is that it is a raw log that the logging companies themselves, the drilling companies themselves, actually use for their processing. And the LAS is, if you will, the Reader's Digest of well logging. I would also like to say that we just released dlisio version 0.2, which is still not a stable release, but it's been serving us rather well, with a massive feature just the other day, which is the ability to read files in what is called TIFF encapsulation for tape image format, which we pretty much had to re-engineer because it's just not documented at all. because in order to make the dlis mess worse, sometimes they come in what is called encapsulation formats, which is an old tape artifact, really, where you have semanticless records that tell you how much data you're to expect in the next chunk, which means that you need to basically layer up the file to read it. It's a right mess. It took months of work to properly do, but here now we are. And one of the files in this file set, namely the mwd.tif, is such a file, which you, in the previous version of dlisio, could not read, but now you can read perfectly fine. So again, I'm going to open the ipython interpreter, which is pretty much what you would find in your notebooks. And I'm going to import dlisio. And you can see from the version that this is 0.2.1. And I mean, dlisio is still under very active and rapid development and fairly well funded. So I would recommend trying to stay up to date. We try and release as often as possible, but they always delay because we want to encompass just that one more feature, right? One of the things that we learned from segyio, which I did briefly mention earlier, is that a lot of users use it as an app, right? And that is something that we try to take care to actually program into the library this time. We want it both to be an effective library for application developers, but we also want it to be useful when you want to, for file exploration. What is actually in this file? How does it piece itself together? Like, what references what? Right, so we have Matthew here chiming in. It's the code that comes off the truck. It can contain multiple runs and a parameter setting when the data is collected, and a lot of tool information that is not typically given to clients in the file. That is very true, and that's exactly what we're going to look at today, Matthew. That's actually very well put. So the first thing that is going to, I would say, bite you is that dlis files don't necessarily have to contain one file. dlis has built into the format this notion of a logical file, which does not have to correspond to a physical file. Probably the reason for that is a lot of logging was done directly to type, and you would want to fit multiple log runs or even multiple logs from multiple wells onto the same tape, because it's a huge clunky physical device that you want to carry around and even just send in the post. And because of that, we need some extra interfaces to work with it. So what you're going to see when you do dlisio.open, and then you do this 206 file, you'll see what you get is a stream, a core stream, right? You got, sorry, what the hell even is that? Oh, sorry, open. You don't even do open. So open in dlisio is much more lower level than in segyio. This is pretty much equivalent to the file open that you would see in just pure Python, right? So in dlisio, we named it load, the function that we want you to use, okay? And what you would get is what you would call a batch, or sorry, what we call a batch. So a batch is a set of logical files, okay? It's and in this case, it's just the one file there, but there can be more. And in fact, it happens quite often that there are more than one logical file. The logical files in a single physical unit don't necessarily, they don't even have to have very much to do with each other. They can be completely separate things. I mean, usually they would be the same thing, but in theory, they can be anything. And there are no restrictions in the format that say they have to belong to the same even logical set of units. It's just that there are more files in this one byte stream on disk. What that means for you is that whenever you're going to load a dlis file, and it's called load because it does more than just opening the handle, it actually tries and query quite a bit of information. So what you would do is that you would do, when you write your program, a loop around the load. Okay, so you would do files, for instance, in dlisio load. Oh, and here's Alan the other developer chiming in. And he says, so from his experience, about 10% of the files have multiple logical files in them. So this is not an unheard of scenario. In fact, it happens often. So what you would typically do is that you would structure your program as a for file in files. Oh, let's actually type that right. And now, of course, it's just one, but that means that you can run the same program for each of the multiple files. Like segyio, we want to encourage good practices when using a library. You want it to feel and behave very Python-y. So of course, this comes with a context manager. So you can do with dlisio.load, and this is how we recommend it's being used, 206.206 dlis as files, and just pass, and this will close the file when you're done with it. So this is how I encourage you to always write your program guarded by that. That means that you will not leak open file handles. However, when you're using it as an app, you kind of don't care, because you know that the second your session is taken down, your file is closed with it, and it's only the one file anyway, most of the time. For that, you can use this nifty trick, dlisio.load 206. This is Python's unpacking, which means that whatever is in this tail, just put it there. And you can actually now check if there are more logical files. In this, there are none. So the length of that is 0, but it can be more. And now f is this file handle, right? But you always need to assume that there are more than one logical file. And you would know you're going to notice, as this is a theme that is recurring with dlis, is that there's always the possibility that there are more than one. So since this is all, since we use this both ourselves, but also encourage other people to use it as an app and as an exploration tool, Alan has written this great feature which is called Describe. I personally believe this is going to be the single most beloved feature of dlisio, full stop. What that really does is that it takes the object that you're looking at, and it returns a string that describes it and a couple of the things that it immediately touches in a very human reporty manner. So note that this is not for machine processing, this is for human interaction. So this is what we get back from the file. It tells us that this object in particular is a logical file. The description of the object is MSCT197LTP, which I have no idea what it means, which probably is just an identification or something. There are 2 frames of data. We'll come back to that, but there are 104 channels. We'll come back to that too. And we find these objects in the file. We also find some unknown objects, and I'll talk a little bit about that. So the basic model of a dlis file is that you have 2 pools of objects. One is a set of dictionaries. Think just Python dictionaries, they're dictionaries. And the other is a bunch of ND arrays. Those are the curves. Now, in LAS, typically you have fairly few dictionaries and mostly just curves, because the rest is either given in a text section or from other contexts, right? There's a little bit of metadata there, sure, but it is largely focused on the curves, and curves as a series of floating point numbers. dlisio has much richer relationship. Dlis has a lot richer relationships between the objects, but at the end of the day, they are dictionaries that just reference each other, okay? And they come with a certain amount of predefined types, which are the ones you can see here, and also some vendor-specific ones. These are beautifully documented in the dlisio documentation, where you have kind of a brief standards reference, and it also references the energistic sites. It does cover the TIFF now, actually, some organization codes. But more importantly, it has a list of object types. And you can see these here that they map pretty much or they're the same that you see here. These are defined by the standard. And we use these to give you a richer experience and to give you a richer interaction with these when we can. So dlis is a lot more structured and rigid in a way than a lot of other formats, because you have these predefined object types that we can actually use to automate a lot of this for you. But it also does allow you to create objects of your own type with the same structure. 440, for just good measure, happens to be the company code for Schlumberger. So this is a Schlumberger file. So one thing you can do now, since we're in the interactive mode, is that you can look at the methods. And I think one of the things that we should look at, this is an internal detail, which for developers is very useful because it allows you to actually debug the objects a little bit. But we have this one special members called attic. End users shouldn't have to care too much about this, but I want to show it now just to emphasize this dictionary structure, because this is the Python equivalent of what this looks like on disk. Actually, this is a terrible example because this actually has them linked. So that was, okay. Because this is an old tape format, it has a storage label, which is pretty much the label that you would put on the box that the tape came in. You would just tape that one on there. And at least in one of the files, this says Schlumberger, I know here, but this is the default storage set. Okay, so let's go back to the file and let's get the, let's just pick one of these. I guess we can pick a channel. Okay, so you do the channels and you see this is dict values. Okay, so this is something that you can iterate over. Excuse me. And this, I think, pretty much illustrates this idea that there is nothing that is just one. Origins is another. The origins objects tell you where this file originates from in some way. So let's actually just describe that right away. But this won't work because the dict values doesn't have one, right? But what you can do is you can do for origin in origin.describe. Oh yeah, there we go. This is actually Schlumberger. This is from the Faro Petroleum something project. I guess even company. Yeah. And this is probably how you should always use dlisio. You should almost always do everything in a loop because there are more than one. Sometimes there's just one, sometimes it's zero, but it's always in this idea of it's a list, right? Or it's a sequence somehow. So you will notice that you will be writing a lot of these unpacking loops, if you will, with dlisio. Even when you're doing it interactively. Of course, this you would probably automate a little bit if you were going to do it a lot, but that's pretty much it, okay? And here you can see the power of this describe, because this is just a summary of information that you can chase mechanically by querying the object attributes as you go, but this does it for you in a human readable fashion. That, of course, comes at a little bit of a performance cost in the pessimistic case, but when you're doing things interactively to explore, that probably is not that big of a deal. He says even creation date 2011. It's pretty cool. So yeah, that's the origin. So let's actually do that, but for the channels. Remember the channels? There are multiple. So what I'm going to do is I'm just going to get the first one. This is a super hack to do that, but I just want the first. I just get the first channel object, which is a theta. So let's describe that. Well, it's the 6-inch frame depth. It's in 0.1 inch. Freedom units are great. The samples are in 1 dimensions. And it has the property indicators of 440 basic, which is probably something that refers to something internally in Schlumberger. they would probably have to confirm that. This you can do for virtually any object in dlisio. If you look at the channel object itself, it has a lot of methods. Some of them are internal, some of them are not. If they are internal, they're either not documented or they're documented as such. Let's not look at the curves just yet. But you can look at its dimension, and you see now you get the list of just one. You say sample dimensions 1. And this is what the describe thing does for you. It has these queries pre-written for you. It has a name. It also has a long name, which can be empty, I think. No, it's actually, yeah, it can be empty, but it's the 6-inch frame depth. And you can see now how when you want to query this interactively and actually just explore it, this is very useful for you. These attributes that you can see is kind of a feature we stole from LAS, where we patch almost that onto, well, actually we don't patch them because these are specified in the standard, but we expose standard provided keys as attributes on the object instead of you having to do this lookup thing, right? Okay. The first time we demonstrated this one internally, we were met with quite a lot of excitement because all of a sudden we found a lot of cool calibration parameters that we hadn't really looked at for that well before. So what I'm going to do is I'm just going to do the same trick again, but now to get the last one. Calibration. And we describe it. So now we even get information on the uncalibrated channel, which is the RGR. We get the coefficients and some measurements, and these refer to, honestly, I'm not actually doing well logging, so I have no idea what the hell this means. But my guess is this is something actually it was referred to before. If anyone actually knows, then please write it out because it'd be really cool. But it's calibration for the gamma ray, right? And you can use that to actually determine, for instance, how you need to process the curves in order to make sense of them, because they could be shifted, they could be wrong, they could be something that in there that you need to be aware of in order to make the right decision or even interpret the data the right way. The tools object typically contain information about the actual tool used to perform the logging and measurements themselves. But now for this, I'm going to show you how you would look up this from a program most of the time, or rather how we do it internally. So there is this get function, which is called object. You can read it as get object. Oh, there we go, Evan. Mechanical sidewall coring tool. Yes, exactly. That's what it is. Okay, well, that's pretty cool. If you're actually know anything about well logging, then of course most of these names will make sense to you right away. To me, they're just indicators, or sorry, identifiers. Sorry, the object function is what we use to directly access specific objects. Objects are identified with a tuple of the object type, the object name, its origin, and its copy. Because sometimes objects are copied around because maybe sometimes they're broken and what have you. But that should give them a different identifier, right? So the sum of those give you the unique key, but half the time the origin and copy number is just 1 in the file anyway. So what we do is that we index them for you, and we try and be as liberal as permissive as possible for you to just look them up. So what you can do is that if you know that you're going to look for a tool, and you know that it has the name sgtp, right? And you can see you get that object back. So let's call it sgtp. And that's pretty great. So that's scintillation gamma ray P. I don't know what the P is, but there you go. Right? So, and the generic name is GR. I don't know what status true means. But anyway, so here's some description for the tool. It has some parts. And these are usually to reflect it in the file somewhere. Also some parameters, which usually are also recorded in the file. What is interesting, and this is an assumption that is very easy to make, but it turns out does not hold in practice at all. Often you will see references to tools that are not in the file, or you reference channels that are not in the file, or there are channel without corresponding tool references in the file, and all combinations thereof. Right? So it's quite often that you get, if you will, orphaned objects. We do provide you a way to get them, but of course you have to make a case-by-case consideration whether or not that actually makes sense, if there's something there, if the file's missing, whatnot. dlisio try not to enforce any of those assumptions onto you. But anyway, so you can use this great describe feature to move about in the file and actually explore them. Here we have, I think, a more interesting attic. Yes. So in this attic, the attic is what we internally use to both stash away stuff, but also store references and what we've read from the file. And what you actually can see here is things like generic name as a list of strings, status as an array of numbers, SGTP, etc. Trademark name, description. You can see all this information is stored in this pretty rigid format that we will then unpack for you, and I would argue provide a much more convenient interface for dealing with. So, for instance, here we have the parameters, and you can see in the attic, parameters. If I could type in the attic, this is now this list of core OB name something something, right? And here you can see from this tool, you can actually get direct link to the parameters. And this is now a list. This is eager. So you can see you can get the SOGR parameter and, oops, describe it, right? And you can now do that for all the tools, which is pretty great. So for param in, we print the describe. Oh, there we go. And here you can see we printed the parameters for all, printed all the parameters for this tool. Temperature selection, surface hole temperature, pore hole status, right? Isn't it pretty cool? So this is all information that is in the file, but is ridiculously difficult to get out. We just printed it for you. Of course, sometimes you want to query some of these parameters mechanically. You want to write a script that would process tens of thousands of files, and you would look for specific pieces of information. For that, of course, you will need to write a lot of loops, because everything is a list, as you will see. And you would have to query it, not with this describe or parse that. You would have to manually write your report. But we have put quite a lot of emphasis on trying to make this ergonomic as a tool, as well as a low-level library for actually reading out the data that are in the files. Right, so Matthew can neither confirm nor deny that field engineers may have been known to copy templates may or may not fit the current tool run. That makes sense. I follow you there. you can sometimes tell that is obviously copied out from somewhere. Even you just reused a different file, updated the actual fields that matter, and if there's some leftover noise in there, just leave that for the downstream user. That's, I guess, fine. We have to deal with it either way. It is a very long old standard with a lot of subtle violations been happening all over the place. Of course, this would be high-level violations. There are a ton of low-level issues as well, but we try and shield you from those. So one thing that's pretty cool, and this is credit goes to Alan Biggin at NTNU, who wrote a paper on using dlisio, where he what he did was he interrogated a file. He looked about it, he poked about in it to see what data is there and what can I use. And I think this is a great showcase of one of the great features, both for exploration in terms of exploring and poking about in files, but also for robust processing when you want to look for specific pieces of information in a lot of files. So this is the code that he wrote. He used a function called match. And if you look at the signature for match, it says filter channels by mnemonics. And what that really does is that it allows you to go over all the objects in a file, and you say, give me the objects that whose name match a specific pattern. And often you know exactly what you're looking for. For what it's worth, it's you have the parameters, and you see there are many, right? And one of the things that the people at Energistics, and I think Ashley Schlumberger did when they created this format, was to add support for something that's called remarks. I will basically be the field engineer that would write down some remarks of what happened, what are the circumstances in this file. And sometimes those we've even seen calibration information about that. Alan here has conveniently posted a link to the notebook that Alan wrote, and we've edited a little bit. But anyway, so one thing you often would do is you would actually consult these remarks, because that's where the field engineer would put information that could help you actually interpret the log. So what you can do, of course, is what we did before, is that we do object, and then we know that this is a parameter, and it's called R10, right? And then we can describe it. This is, of course, pretty useless. So let's actually do the describe is useless, but what you want is the values. And this is actually just empty. So what he did, oh yeah, that's a very good point. There are two Alan, the developer and the acoustic scientist. He works with ultrasound at NTNU. Usually when I say Alan, I'm going to refer to the developer, who's a colleague of mine. But my apologies if I get them mixed up. Okay. So what he wrote, a feature that we had tinkered with for a bit, and that he made great use of, is the one that's called match, because sometimes you don't want to actually manually filter, but you know that you want to actually have a look at objects that match a certain pattern, which is perfect for this remark. So what you can do is you can write a regular expression, and now of course know what to do, because I know that the names of these remarks are 0 through something, but I assume that there are less than 100 remarks, and I know that they're of the type parameter. Okay, now you can see what I get as a generator. So I can do for remarks in, just to get the list. For remark in. And you can see I actually have quite a few objects. But they all start at 10 because my regular expression is wrong, right? So I can do 1 and 2. This is a regular expression that should now match all the remarks objects. You see now we have 17 of them. Yes, 17. They happen now to be in the wrong order, so we'll just reverse them. And what's now cool is that we can actually go over these remarks. Remark in remarks, and we can just print the values like we did before. Of course, this is awful, right? But here you can see we actually log objective obtains sidewall cores from the well. Very good, Evan. It's definitely sidewalling. Tools run per sketch, 25 attempted cores, recovery was, and then what else is going on here, right? But it looks like this is the second one. Sorry, third one. So let's get that. Remarks, 3, and then the values. We can strip it maybe to remove, and you see this is an NumPy array. So these are still arrays, right? We're going to come back to why that is the case, but these are fixed length strings. But you are able to turn these into strings. I think maybe like this. No, because I would just get the array. Value is 0. I think this can turn into a string. Yes. And then strip it. Right? And now we can actually do this for all of them. The recovery was %. So of course, if the field engineer does not actually record anything useful, it won't be useful to us in the log either. But here we have been able to, in 3 lines of code, to be able to actually decode what was there. And this you can do mechanically for thousands and thousands of files, for instance, to just survey where are the interesting ones, in addition to doing this interactively. All right. We've talked a lot about the dictionaries now, and all the objects of different types have specific fields that are specified and some that are not. But I'm not going to focus anymore on that, because that I think is something that you can just do to explore when you actually have data that you're curious about. We're trying to make this as discoverable as possible, but the documentation is a great help there. One thing that is very interesting is, of course, the curves. That's usually what people want to dive into. Of course, to make sense of them, you need to make sense of the metadata, which you now actually have. But the curves is where the real juice is. Usually, when you write a library like this, you want to try and shield the user for as much detail from the format as possible. But one thing that we really can't, just because of how the file is structured, is to shield you from the idea of frames. So in dlis, data is organized in so-called frames. Now, a frame is a series of consecutive samples done over, well, with 1 through to many tools in so-called channels at the same time, which is pretty much the on-disk equivalent when you have multiple squiggles lined up next to each other. Okay, so it's a set of columns, but they're recorded row by row. This pretty much would be like, I often like to think of physical analogies when dealing with that. And you can imagine when you have multiple pens really moving as you're moving tools up and down the borehole, all writing to the same long strip of paper that you're just pulling, right? From all the disaster movies when the seismographs are picking up the earthquakes. And that's how they're recorded on disk as well. And we have to reflect that in the interface, because otherwise the program would just be too slow. So the important thing to really take away from that is that data is organized in frames, and you should always go via the frame and not try to think about the channel. To make that easy, we of course have the frame object directly onto the file. And you can see there's now dict values of 2000 in T and 800 in T. So let's do frame 2000, okay? Which would then be actually for like all other objects in dlisio, it can be described. And here you get useful metadata about that frame. And you can see it's indexed by time. The interval is 3 million something. The direction is increasing, which means the number should be increasing. It has constant spacing at 2000, and it's indexed on time. It also has 4 channels, sorry. It's time, depth, and SL, which honestly, I have no idea what it is, but we're gonna be able to discover that in a bit. So one thing dlisio then does for you is that you do the F2000, you can see it has all these members, including the channels. And this is now a list of references to the actual channel objects. And I say go to the frame first, and that is not an accident. So what you can now do is actually for the channel in F2000 of channels, you can print the channel description. SL is the station logging depth. And you can see the time is 1 second river time. It's in milliseconds. The cable tension, I guess this is, what even is that? It's pounds, is it foot pounds? So Newton, but for Americans, I guess. And some more inch stuff. Anyway, this is actually the boring of the two, so I'm very glad I started with the 2000. But it's also the one with the fewer channels. So you have actually direct access to the channels here, and that means that you, from that channel too, can look at the properties. Now you can look at the source, for instance, and all sorts of cool, and even the parameters. So you can use that to change the parameters directly from the frame. And this is where dlisio is trying to be very useful, both programmatically, because what that means that you're able to do is that you can do for frame in frames, you can do for channel in channels, for parameter in parameters. Oh, all the way around. You can now actually print the parameter 9. Isn't it parameters? Is it parameter maybe? Excuse me. Source parameters. Isn't it the right one? Frame, channels, channel source. Isn't that what I did? Let's see. Oh. Is it empty? Where did I miss the parameters? Oh, did I iterate past maybe? Oh yeah, of course I reused the name. I'm so sorry. Anywho, you can essentially write programs like this. I'm pretty sure I'm going to get a scolding from Alan for messing up which one it is. Channel name frame channels. So if I do it. Oh, right. That might be it then. If anyway, you see pretty much where I'm going with this, except that I'm getting an untype in one of these. Not all channels have recorded source, which is also a charming detail that you would get from dlisio. So of course, you would need to put in guards for actual processing programs there, but it allows you to do this in a whole on whole sets of files because they're still reasonably structured. Okay, anywho, what I was going to show is that you can use the frame to chase all kinds of useful data. We're at 2000 still. But what you would usually want is the actual data itself. You get that by calling the curves function. This looks, oh, is it parameters maybe? No, oh yeah, that might actually be it. No. Because it was channels of source. Anywho, we can revisit that if we have time at the end. So what this gives you, look at the curves, and this I'm very happy about, is if you look at the type of that object, it's an ND array. So like in segyio, we wanted to give, when we actually came to data, a pretty no-nonsense access. And this ND array is the full frames data, which is pretty much a data frame, but it is a little bit more low level because it doesn't have all the, oh, is it, if that's wrong. Oh, right. Right. That was very embarrassing. So what you can see here is that from this snippet of code, which is just 3 nested loops, you're able to print all the parameters that goes into describing the channels in the frames in the file, right? And of course, you need to guard for stuff when it isn't there. But it comes to show how you can mechanically scan thousands and thousands of files for this kind of information, right? So yeah, that's pretty cool. Okay, so we have this curves object, which has a shape, and you can see it's a 921. And these are rows. So there are 921 rows of data in this. Now, this is just an ND array, although it is what is called a structured array. Because if you look at dtype, this, you'll notice it has this pretty clunky format of tuples. But it has the frame number, and these are our identifiers for time and also their type. Now, remember how you, in well logging, often draw these curves and you do them side by side because, of course, there's a vertical direction in which you're logging, or horizontal, I guess, at some point. They're stored that way in the file, and we're presenting them to you that way. The structured array is kind of a pandas light, or maybe the other way around. Pandas is a very beefy methods on top of the ND array. Yeah, I think it's actually the ND array that powers pandas. Now, what it allows you to do is that you can filter out, for instance, on these columns. So here we have just a frame number, right? So this is which number is the frame as we're going down, which record is this? And in fact, if we do dtype, it has something called names, which are the columns here. You can even do the same thing for time. And here you actually have the timestamps for the log. Of course, since this is a NumPy array, what if you just want the first time? Or what if you want the first, well, you want the frame number as well as the time? Well, I mean, you just ask for both, right? And then now you get a sliced smaller array. This is a very powerful way of working with well logs. Let's actually do something cool here. So it's from import matplotlib.pyplot plt. Oh, matplotlib. So what you can do here is that you can actually plot. Let's see, actually, go back to the, look at the names. So this tens SL. Plot, and then you can do the curves, tens SL. But you want to do it from 200 to 250, for instance. And 3, 2, 1, let's draw. Oh, there it is. And with that, we have a plot. Now let's think about this for a second. So now we've actually been able to take open a well log in a format that has been pretty much a black box for almost 3 decades. And we have, in 3 lines of code, been able to plot a subsection of that curve. And what if we don't want the tens SL, but you want the depth instead for the same range? I guess this is not as interesting because, I mean, look at this. But this is not something you can do. This is how easy it is to get and even plot multiple sources of that data together. And you can do this in loops. Credit here goes to them to the NumPy developers for the structured arrays, which is the perfect feature for a library like dlisio, because it gives you this powerful interface to slice and dice this data as you like. You can plot it, reverse it, you can subsample, you can do whatever maths you want on it. And all we have to do is to provide you the record as it is on disk. And our interface to that is really just the frame.curves. Just give us the curves that belong to this frame. Now, I want to emphasize the frame thing in here because actually, let's look at the other frame just to illustrate that, because this one was so tiny. So let's get the last one. this super hacky way of getting it. It's convenient for me, but it's not something you want to do in your script, because in your script, you want to do this over all the frames anyway, right? So let's look at that one, and then let's look at the channels. And you see this one has a lot of channels. It has 43 of them. So let's get the curves for that, shall we? Sorry, it is this curves. Oh, 2,300 rows of data in this frame. And if you look at the D type and the column names, you can see there aren't many here. Each of these channels have longer names that are their descriptions. Let's, with that too, you can do curves, and we can actually print them. And of course, you can slice this however you want. So let's actually just get from 10 to 50. And then we only want the HV and the skr. Oh, is it the other way around? Yeah, there we go. Then we get 10 to 50. So yeah, I think that's pretty great. That's pretty cool. And this is a feature, again, which is all NumPy. And I think that's one of the more appealing things about dlisio, is that it doesn't get in your way when it comes to the actual data. So we have a question here. Image logs. Are dlis the standard for image logs, and are they accessed differently? Yes. Dlis, or rather, when we get images, I've never seen it not be in dlis, but that is really something for someone else to answer. But I think in practice, yes, dlis has first-class support for image logs. And we do that, I would argue, really, really well. And we do that well largely because of NumPy. So we actually have a file with that. If you look at the notebook link that Alan Horstad posted in this channel. Oh yeah, Matt, same question about 2D, other 2D logs like spectral gamma and acoustic spectra, sonic scanner. Yes, all of those. They enjoy no particular support from dlisio in the sense that we don't pick them out or even name them image, but you can look for samples that are multidimensional and not one. And in fact, that's one of the things that the notebook that Alan linked to and that Alan Wiggins from NTNU Piper actually discusses, is exploring a file with acoustic image logs. They are accessed the same way, except now when you access this sample, it will be not a singular value, it will be an array again. And this can go as many dimensions as you'd like almost, which of course is a right mess to implement, but it's a really powerful feature. I think actually one of the files here might be one. Yeah, this F15 actually is exactly that. So let's do that. We open or we load this new file. Okay. dlisio.load F15. Right. You see this file is pretty big. It is, well, I mean, pretty big, 140 megs. So it wasn't that big. We have some more questions. So Schlumberger use dlis exclusively for data collection. If it is their log, it's in dlis. Okay, that's very interesting. Other non-Schlumberger companies use dlis? Yes, certainly they do. Do they use it correctly? No, they don't. I mean, that's maybe a little bit harsh, but we see a lot of weird files with very non-standard behavior, which fortunately with dlisio, you don't get to notice too much. But okay, I'm actually going to go into that particular notebook and hijack some examples because they're really cool to just show and explore. Does this even render? Honestly, this is mostly to get, oh yeah, this is actually pretty cool. And we didn't even cover it yet. So loading this file and then doing describe on it actually prints a warning. It says unable to decode string. So that is an issue that we puzzled over for a very long time. But it turns out, so in dlis, it says that you're only really allowed to use the ASCII alphabet, right? So you're only really allowed to use English letters. Of course, nobody cares about that. So they use degree symbols. They use, I mean, I work for a Norwegian company, and we have a field that's called åsgård, which is impossible to spell in English. So at some point, these non-English things sneak in. By default, we assume that a file is compliant. And if it is compliant, there are no problems. But sometimes files are not, like in this case. And it is, you can see here even that it has the double quote and then single quote and N and E. So these are obviously coordinates, and then this B0. I happen to know that that is used in European encodings for the degree symbol. So what we have is that you can tell dlisio, I want you to try this encoding for strings. Okay, so we have a feature called set encodings, which take pages that Python knows about, like Latin 1. And they say, I want you to try these encodings in that order. And the first one that doesn't fail when you try and decode strings, that's the one you're going to use. Now that symbol happens to be invalid UTF-8. So we even want to try UTF-8 first. And actually, let's do that. Let's try just UTF-8. You set the encodings, do the describe. Oh, actually, that one happened to be okay. I didn't even realize that. So that's valid UTF-8, but quite often that's not the case. Then you want to try Latin 1, for instance. That's also a pretty common encoding. Technically, that's a standard violation, but we want to handle it anyway because it's so common. But this is something you need to opt into and say, please decode strings as if they were. I know this one too should be Latin 1, so let's put it to Latin 1. Latin 1. And now to describe works perfectly well. To unset it, I think you just pass it the empty list. Okay. So let's go here. Okay. You can see this is Aaron's notebook. I recommend everyone to actually carefully read through it because it is amazing, and it shows you how to really dissect a file and use information you find in one table to chase information in the next. We're going to skip directly to the frames. So there we go. So which one we want? We want the object. We know that we want a frame object, and we want the one that is called 20t. No, sorry, 20b. You see now we get that frame object, right? It can be that easy. If you know exactly what you're looking for, then you can look it up directly like this. So if you describe it, you can see the channels it has. You can see the spacing. And this now is decreasing, for instance. It's indexed by the borehole depth. Pane channel, blah, blah, blah. And here actually you can see the plots that we will be able to make at some point. I figured we wanted to look at this one. It is called the WF1. we get the curves. Sorry. And then you can see, you can get the WF1 curve, right? And in his case, I think he uses 12,300 and then out. So this is the depth he's starting at, right? But of course, here we can also use or we can plot that even if you want to with time, I think. Isn't it time? Curves.dtype.names. T-depth, it's depth, of course. And you can see there's a lot of, this is dlis for 0 or undefined. This is pretty cool. But here's there's just a lot of numbers, way too much for any human to actually deal with. So then what you can do is that you can do the plt.plot and then 12,300 You see this, I think, is all the data in there. Oh no, it's still just a VF1 actually. Eventually you're gonna get to a plot like this if you follow Alan's work. Oh, right. There we go. I don't know why that does not focus immediately, but here we go. Anyway, so this is at the depth index 12,300, where we plot the waveform. What is cool here is that you look up this is an image. Because there I look up a singular value in this array at that specific column, and I still get a full array back. So this, hopefully, Evan, doesn't necessarily answer your question, but it shows you what an image log looks like in code. So this is at the depth index of 12,300, and you still get a full image around it. And of course, to interpret this, you would have to look at how is the channel calibrated? What does that actually mean? But now you have the tools to do that. And I would honestly, with all my heart, recommend studying Alan and Alan's notebook and mine a little bit. For a reference there, because it's very thorough and it comes from this user perspective, which I think is very useful, not the developer one. All right, so we have about 15 minutes left. I have shown most of the things I wanted to do. If there are any more questions, any things you'd like me to show, to talk about, reflect on, then I'm of course happy to do that. I will also be available later if that's interesting, and if not, then I think we'll call it a night. Oh yeah, and I've been notified there's a little bit of latency here, so there might be an awkward pause right now.